So class, today we are going to cover a topic from magnetostatics, the Amperes law. But before going into the details of Amperes law, let me give you a very brief analogy between electrostatics and magnetostatics. And by electrostatics, I meant to say what we have already been covered in the previous classes. Uh, we are aware that for highly symmetric charges, how to calculate electric field or the electric forces. Definitely we calculate electric forces using the Coulomb's law, which is just a restatement of Newton's universal law of gravitation in electrostatics. While Gauss law is a more generic uh, statement of Coulomb's law, we know that if we have a symmetric charge distribution, say planar, circular, spherical or cylindrical, we can use Gauss law and exploit that symmetry to find electric field at a certain point inside or outside the region. By inside I meant to say inside a Gaussian surface, over a Gaussian surface. And we know that we can also derive Coulomb law from the Gauss law, but the converse is not true. That's only of the reason that Gauss law is a more general and more natural formalism of electrostatics. In the similar fashion, if we have to find the magnetic field, what we can use, what we have available tools, we know that magnetic field is originated from a current carrying wire. That is, a changing current in a system in a wire can produce magnetic field. So magnetic fields can be calculated for any distribution of charges, and such magnetic fields can be computed via Amperes law. It is named after a French physicist André-Marie Ampere. So this is also called Ampere's circuital law. And this law can also be derived from a more general formalism of magnetostatics, that is Biot-Savart law. We will study Biot-Savart law in future sessions. So let's see uh, Ampere's law is and how to calculate magnetic field. So first of all, exploit the symmetry of the system as we usually do in the Gauss law. That is, understand and figure out what the symmetry system has. Either it is planar or spherical or cylindrical. Because if the system is symmetrical, or we exploit or find some sort of symmetry in the system, it would be a very easy for us to find the magnetic fields. Then distribute or divide your line element, your current carrying wire, into infinitesimal small differential line elements of length ds, and each that line element will have a differential magnetic field dB. So D is for a differential, and differential stands for a very infinitesimal change, a very small change. Now sum all the contributions from all the line elements. That is, how do we sum in such a system? We integrate it. So on the basis of all systematic procedure, it states that the line integral of magnetic field around any closed path, I'll reiterate quote unquote, its closed path, the line integral of the magnetic field around any closed path is equal to mu times the total current enclosed by that curve. So the dot product of B and the line element equals the mu times the total current enclosed by that loop, and such a loop is called Amperian loop. So you might remind of the Gaussian surface around a charge distribution. So in the same fashion, we draw an arbitrary or not arbitrarily, we draw a hypothetical loop around the current carrying wire, and that loop is called an Amperian loop. So definitely the shape of the Amperian loop depends upon the symmetry of the system. So there's another statement of just a mathematical statement of Amperes law, that I rewrite the dot product in terms of cosine theta. So this cosine can be the angle with ds or with b. So but usually we write it with b, so that is, we only include the horizontal component of the line element, that is the component which is along the direction of line element. so which comes out as B cosine of theta times the line element. As shown in this diagram, we have three wires. There are some dotted circles, there are some crossed circles. So there are two types of current carrying wires, either into the page or out of the page. And we are considering the counterclockwise direction. As you can see, this is an Amperian loop. So this is an arbitrary shape of an Amperian loop. So definitely it will correspond to some sort of symmetry if we are really dealing with such a system. So suppose the wires are cylindrical, so I will draw just a circular or cylindrical Amperian loop here. So the line element is just along the direction of integration. So in the same fashion, um, magnetic field is some sort of tangent to this line, to this loop. So this is so the direction of this loop will give you the direction of the magnetic field. I'll elaborate this point in a minute, that what do I mean by the direction of the magnetic field or the direction of the loop. So this is just to give you an idea how to draw an Ampere loop. All the current carrying wires that are included in the loop will be included in the calculation, and all the wires Ci3 will be excluded. They won't have any effect on the net magnetic field that we calculate using the Amperes law. So the next point is about the sign of magnetic field. What would be the sign of magnetic field? Either it is positive or negative. So initially we do not have any need to know the direction of magnetic field before integrating. So we assume the direction of B in the direction of integration. So usually we assume it to be counterclockwise by convention. So then it's positive, we get rid of an extra negative sign in the calculation. After integration, use the curled straight right hand rule to assign a plus or negative sign to each of the currents. And so let's see, what do we mean by curled straight right hand rule. It's very easy to understand. So you have been shown a diagram here, a current carrying wire and an Ampere loop. As I have told you, the direction of integration usually we adopt is counterclockwise. So curl your fingers of the right hand in the direction of the Ampere loop. So this will be the direction of your magnetic field. Now see in which direction your thumb will point. If your thumb points up in the upward direction, it shows that the direction of current will be positive. If fingers are curled in a clockwise fashion, the direction of current will be negative. So in this way you can assign the positive or negative sign to the magnetic field. So just understand it with an example. So we have to find a magnetic field outside a straight wire, um, definitely current carrying wire. Current carrying wire is shown here, this wire I. So draw an Amperian loop of length of radius r. So the magnetic field would be the same at all points upon the surface, upon the line element r. So as the wire is cylindrical, so this loop is also cylindrical. Um, Now integrate clockwise, counterclockwise, to retain the positive direction. So the line element will be tangent to this loop. So definitely we will assume the direction of P also to either parallel to the ds or anti-parallel to the ds. So for simplicity we will assume theta to be equal to 0. So again it's just a matter of convention, and it will allow us to get rid of an extra negative sign. It will make calculation a lot easier to understand. Okay, so note that B and DS are tangent to all points on the loop. So either B and DS are parallel or anti-parallel to each other. I arbitrarily assume that theta equals 0, that they are parallel. So cosine of 0 will be equal to 1. So now it comes to the calculation part. By using the Amperes loop, B dot ds equals mu naught I, exploit the dot product, put the angle theta which is 0 degree, it comes out BDS. B is just a scalar number and integration around a loop, so B will come out of the integral. So this is the line element of the cylindrical Amperian loop, and we know that the circumference or the line element of a cylindrical surface is 2 pi r. So this is just the circumference of the circle. So it shows that B is equal to mu naught I by 2 pi r, and this is the same result we get from the Biot-Savart law. So that is, magnetic field is inversely proportional to the distance 1 over r. and the direction of I can be found out using the right hand rule. Again, just curl your fingers in the direction of the magnetic field, thumb will point in the upward direction, so I will be positive. And this is all we have from this example. Thank you.